Hello and welcome to another video lesson with Takoa Lawson. Today we're going to be looking at some example problems for the circular motion unit. The next problem that we're going to look at is a car driving around a circle on a level road. In a lot of ways, this is similar to the mass on the turntable that's rotating. The only difference is, instead of the ground rotating and the mass sitting on top, the mass is now driving around the path it would take if it was at rest and the floor underneath it was rotating. Still same information. We've got a radius of curvature, we've got a mass. When we think about the forces acting on this object, if we were having a free body diagram of this car, we're looking at it from the top view. I'm going to look at it from the side or from an angle where I'm looking at it from behind the car. We would see the force of gravity pulling straight down. We would see the force of the road, which is a flat horizontal road, pointing straight up. So we'd have a normal force and a force of gravity. And then we'd say, oh, those are the only forces acting on it. But it can't be. It's going in a circle. So once you're going in a circle, there has to be a net force towards the center of the circle. So the question is, what force is going towards the center of the circle? Well, in order to turn in a car, you have to turn your wheels, and the force acting on the wheels is friction. So there's a force of friction going towards the center. And what you should notice is if you were to look at this free body diagram, whether or not it's friction holding the mass going in a circle from it driving on the road, so it's friction between the tires and the surface, or because the surface is rotating, so it's friction between the tire and the surface, actually results in it being the same situation. So what we see here is the normal force is equal to the force of gravity, again, of course, mg, and the force of friction, because the tires are not slipping, you're not skidding, is still a static friction. So the force of friction is still less than or equal to mu mg, unless we're trying to figure out, again, the maximum speed. Since the vertical forces cancel out, we see that the net force is actually the force of static friction. So we see again the net force, or the centripetal force, is equal to the force of static friction. Now, it's less than or equal to mu mg. So it could be a value smaller, but we notice the question here is, what is the maximum speed that we can take this at? The maximum speed means we're going to be at the maximum force of friction, right? Because if you're at the maximum force of friction, that's as much as friction can do. If you go beyond that maximum speed, you'll slide off, or you'll continue in a straight line, because you'll end up running into kinetic friction, and kinetic friction is always less than static friction, so you won't be able to continue in a circle. And that's why it's dangerous if you take a turn too fast and you lose grip with the tires. You pretty much have no chance of being able to regain it, and you'll see skid marks from when cars have gone too fast around a turn, where they basically just become straight lines once that centripetal force is no longer available. The force of static friction, and it equals that because we're at the maximum possible speed, and the centripetal force is equal to the mass times centripetal acceleration, or mv squared over r. And now with this relationship, I'm solving for, oh, you notice these are the same mass, so they cancel each other out. So it turns out mass is irrelevant. So I'm trying to get the maximum speed. That's going to be my v variable here. So I'm solving for v, so we multiply both sides by r and then take the square root. And so v max is going to equal mu s times g times r, and then we take a square root. It's going to look relatively similar to some of our other v-mins and v-maxes for these circular motion problems. Hopefully at some point you'll start to recognize it's pretty much the same thing. Draw a free body diagram, figure out what the net force is. There has to be a net force if you're going in a circle. That net force is equal to mv squared over r. Next, we're going to look at a ball being rotated on a string. So before we had a mass being rotated on a turntable that was rotating, then we had a mass being rotated because of its tires in contact with the surface. Now we have a mass being rotated because it's attached to a string and it's being whirled around. You'll notice in each of these cases, they're all masses moving in circles. The only difference is, and actually in the last two cases we didn't have a difference, it was friction causing it to go in circle both times. The only difference with this problem is that our mass is going in a circle is not doing it because of friction, it's doing that because it's a force acting along this rope or along this string, which is going to be a force of tension. we can look at this free body diagram for our ball, and it's an isolated ball. So the fact that it's an isolated ball means there's nothing else around it. It's not interacting with anything other than the string. So what that means is that there is no force of gravity. It's not on a table. There is no normal force. So the only force acting on this ball is the force acting along that string, or the force of tension. Now that we know the force of tension is the only force acting on the ball, it's relatively straightforward to see that the force of tension is equal to the net force, which is equal to the centripetal force, which is equal to mv squared over r. We're given information about the mass and the radius and the maximum force. And so when it says, what's the maximum speed the ball could be whirled at, what they're really saying is, if we were to solve this for v, so if ft equals mv squared over r, then v is going to equal the square root of ftr over m. You'll notice r is a constant. You'll notice m is a constant. So really what determines the velocity is the force of tension. If you had an infinite force of tension possible, if this string was unbreakable, then there would be no limit to how fast you can whirl the ball. However, we're told that if it exceeds 274 newtons, then the string will break. So what's the maximum velocity we can whirl this string at without breaking it? So what we're really saying is, oh, what would the speed be if the force of tension was 274 newtons around my radius of 0.89 meters for a ball with a mass of 0.150 kilograms? And we find out that the V for that force of tension is 40.3204, going to 2 sig figs, it's going to be 40 meters per second. This is a good place to emphasize that if you're at a point on the circle, we don't know which direction we're rotating, but let's say that we know that the ball is being rotated in counterclockwise direction. The velocity is tangent to the turn. The velocity is tangent to the turn at that point. If the rope were to break, the ball would continue in a straight line. If they were to give us any imaginary location and then tell us that the rope broke at that point and ask where would the ball go, then we would always predict that it would go in a straight line that's tangent to the curve at the point where the rope breaks. Or another way of saying that is that if we had a target that we were attempting to hit, we wouldn't want to release here because that would go away from it. What we'd want to do is find a point where tangent to the curve would hit the target. And so this is where we'd want to release the ball at to make sure that it hit that target. Next, we're going to look at some problems that could be constant motion or could be changing motion. In this case, it's still going to be a constant velocity, even though it could actually rotate at different velocities. And for the next problem, we're going to talk about it being able to speed up or slow down. However, in this case, we're actually rotating at a constant speed, but we're on Earth or we're near Earth. It's not an isolated system. Other forces are acting on the objects here. If this was a ball being rolled around a circle, we couldn't just say there's the force of tension. We'd have the force of gravity because it's also Earth acting on it. So the first question is to draw a free body diagram for the passenger at the very top. So we're looking at this top location, and at the very bottom, so we're looking at this bottom location. If we were looking at the top, there's one thing that's obvious. There's the force of gravity, right? We're near Earth, so there's weight or gravity pulling downward. Now there's a temptation to make the normal force equal to the force of gravity. That can't be true here, because we're going in a circle. There has to be a net force towards the center. There has to be a centripetal force. The sum of the forces along the radius have to point towards the center. The downward force, which is the force of gravity, points towards the center. The net force has to be down. So the upward force, which is the normal force of the seat on the passenger, cannot be equal to or greater than the force of gravity, because if it was, there'd be no net force down. So the normal force has to be less than the force of gravity. We're going to see some extreme examples, which is as you increase your speed, that normal force has to get smaller and smaller because you need a greater centripetal force, but the force of gravity is constant. You can't increase the force of gravity, so there's some interesting consequences of that fact. When we look at the bottom, we still have the force of gravity straight down towards Earth. And the force of gravity is the same. It can't increase or decrease. It's a constant unless we change the passengers, unless we change what the mass is being acted on. So now, at this point, we have to have the net force towards the center of the circle, which is up. So the net force going towards the center means our upward force has to be greater than the downward force. That means the normal force here has to be greater than the force of gravity in order to create this centripetal force, or the net force towards the center. Let's look at that same Ferris wheel problem. But as I mentioned before, let's allow its speed to change. So we're able to increase and decrease the speed of the rider. If we look at that top free body diagram again, we saw that the force of gravity has to be greater than the normal force. Now, the normal force is the ride pushing up. The risk is if you start going faster and faster, that net force gets bigger and bigger. The normal force has to shrink to be able to make the force of gravity grow to be that net force. But the force of gravity is constant. There's a limit. At some speed, at some maximum velocity, when you reach that maximum safe speed, the normal force will approach or go to zero. Because once that normal force is zero, you're no longer in contact with the ride, and then you lose contact with the ride, and you become a projectile, and you move tangent to the circle, or you're launched off of the Ferris wheel. The question is, how can we define or describe that maximum speed? It's going to be very similar to our other problem, except for in terms of not using force of tension and not using force of friction. In this case, we see it's the force of gravity that's responsible. I'm going to go ahead and leave the net force in it just to be able to describe it at first. I'm going to choose up as the positive direction of this argument, which is important. That means the normal force, which is up, is positive, the force of gravity, which is down, is negative, and at the top of the circle, towards the center of the circle is down, which is the negative force. So when I say the net force, in this case, it's going to be a negative centripetal force, and that's going to be equal to mv squared over r, or negative mv squared over r, and that is going to be equal to the normal force minus the force of gravity, or mg. We notice this would be just to solve at a specific velocity if I wanted to figure out the normal force, or given a specific normal force, what would the speed be? But I want to know the maximum safe speed, and the maximum safe speed happens when the normal force approaches or falls to zero. That means this cancels out. Vmax is actually negative mv max squared divided by r is going to equal negative mg. We notice a couple nice things. Negative m divided by negative m, gone. Vmax squared over r equals g, or Vmax equals the square root of rg. Turns out that the maximum velocity, as you're going over the top, where it's gravity holding you in, is the square root of rg. We're going to see a couple of other situations where it's again going to be that same idea, the idea of a maximum speed. We're also going to see some situations where we have a v minimum speed. Turns out a lot of times we're going to get that same square root of rg, and you notice when we're looking at the coefficient of friction, when we're talking about that velocity, we saw we just added in the mu there. The maximum speed that you can travel on a ride where you're worried about gravity being what holds you into a circle is square root of rg. Now notice, if this was a roller coaster and we were traveling on the inside of the loop, then the normal force from the track would be pushing down. And if the normal force from the track is pushing down, there is no Vmax. There would be a V min in that case if I wasn't going fast enough and gravity was too strong. It would actually pull me out of the circle and I'd fall on my head. So you have to be a little bit cautious. In some circles we're talking about V max, in some circles we're talking about V min. We're looking at the force from friction, there was a V max. When we're looking at riding in a Ferris wheel, it's a V max.